over 2,000 years, programming has evolved from calculating star positions to calculating complex math formulas. What is programming, though?
Computers function by following sets of rules. Programming is the process of using these sets of rules to solve problems. These programs tell computers what to do in their own specific language. Without these programs, a computer would be nothing more than a piece of plastic, metal, and silicon. Here is an example to help you understand the concept of programming more. Imagine going to a cafe and ordering a sandwich. All you would have to do is sit down, tell the waiter what you want, and he will get it to you in a short amount of time. Now, if you had a robot as a pet and decided you didn't want to go out to eat for lunch and instead have your robot make you a sandwich, you could ask the robot to make you a sandwich, but nothing would happen. As you did not give the robot specific programming to make sandwiches, it cannot help but stand there, unable to compute your command. If you knew the robot's programming language and also understood how to reprogram it so that it can follow a new command, then it would go into the kitchen and make you a sandwich, as per commanded. This is why we need programming. If there were no programmers, we would be unable to visit YouTube, make Word documents, solve mathematical formulas in less than a second, create functioning spacecraft, or any of the many other jobs and activities involving computers. It would be like traveling back to the Stone Age. So when did programming all begin? The first sign of programming activity brings us back to ancient Greece, circa 70 BCE, where the Antikythera mechanism was created. This device was designed to predict what the positions of the sun, stars, and moon would be in the future decades. It was able to calculate the lunar phases, planet movements, and eclipses as well. The mechanism was lost in a shipwreck off the coast of a Greek island known as Antikythera, and subsequently found in 1900 by fishermen. Many have pondered its existence, as on the item was an instruction manual, depicting how all of the pieces inside were rotating. Although this mechanism is the only one of its kind to be found, many ruins around Greece tell of many more being created. Jumping forward to 1801, Joseph Marie Jacquard invents the Jacquard Loom, which is a device that weaves cloth. This loom used punch cards to perform a sequence of operations to control the weaving looms. These punch cards could be switched around at any time if the pattern design had to be changed. There could be up to 400 holes in the card, and the way it works is actually pretty simple. If there is a hole in the card, the hook above that space would be lowered down through it and lift the thread beneath up. If there was no hole in an area, the hook would stay up and the thread beneath would stay where it is. These punch cards are considered an early example of the principles in computer programming. Later on, in 1841, Ada Lovelace and Charles Babbage began to work together on Babbage's Analytical Engine, which was practically a computer apart from using cogs and gears to work instead of electrical bits and pieces. Lovelace looked at his designs and added her own notes to them, essentially creating the first computer program. She predicted that the machine would even be able to compose complex music and be used for scientific and practical purposes. Although the machine was never completed due to lack of funds, it can be seen in London's Science Museum. John von Neumann proposed the modern form of the CPU's design. His work led to computer designs that were able to store programs and have a self-modifying code, which made the long, tedious task of reprogramming the computer not have to happen so often. Since the 1800s, programming languages have evolved with the technological advances, keeping up with the modernizations of computers. We are going to look at how different codes and languages have developed since von Neumann, Lovelace, and Babbage. When several pairs of computers want to talk to each other at the same time over the same network, this would cause a data collision if not for the switch. Imagine a line of computers, A, B, C, D, E, and F. B and E wish to connect to each other, so a switch forms a connection between the two, BE. But if BE and CF wish to connect at the same time, the switch forms separate networks between B and E and C and F, allowing them to connect at the same time as the other connection without slowing down the network. If BE is in a connection, however, B cannot talk to A at the same time as E, as the connection is only between B and E. A patch lead is a cable that connects a switch to a computer or a switch to another switch. Switches have evolved from simple, semi-intelligent devices that could mildly understand which hosts were connected to which ports and how to retransmit them correctly, into devices that know how to route data quickly and efficiently, as well as having multiple ports that allow for not only several fast Ethernet connections, but also some other higher speed connections. Machine code is the lowest level of programming language and the only language understood by computers. Although this language is easily understood by computers, it is almost impossible for programmers to use, as the language consists almost entirely of numbers, binary to be exact. Assembly language is a low-level programming language, just slightly above machine code, that uses more memorable mnemonic, or simple memory aids, codes and labels to represent machine-level code. It contains the same instructions machine code does, but the instructions and variables have names instead of binary. Each instruction corresponds to one machine operation, and the assembly language is translated later into machine code by an assembler program, using translators that convert the high-level or assembly languages into machine code, using words and symbols that the programmer can remember more easily than long lines of binary. Higher-level language is a programming language that resembles a natural language. Each instruction translates to many machine code instructions and is problem-based rather than machine-based. Fortran was the first of the high-level languages to be developed in 1954. However, these high-level commands must be translated into machine code before they are able to run. There are two ways to go about this: converting the code all in one go, or one instruction at a time. In the former, the language is translated into assembly or machine code by a compiler, which is translation software that converts the high-level commands, or source code, into machine-level object code before trying to run the code. This object code is produced as it can be saved and runs independently of the translator and source code, taking up less memory as it is running much faster without the translator's presence required. In the latter, an interpreter converts the code one instruction at a time into machine code, running it first as a test before moving on to the next instruction. There is no object code in this procedure, just source code and translators. This approach is more useful when one is developing a program, as it checks for errors and stops if it reaches one. But it requires a translator to be present, so is generally much slower and takes up more memory. Modern translators often have integrated development environments, or IDEs, that help identify errors in the code as it is being developed so as not to cause any backups when an undiscovered error shows itself. IDEs have several features available when they are editing the code, such as code editors. A code editor is a text editing area that helps organize the source code by managing the layout, by indenting or color-coding command words, variables, and comments so that they are easily identified when needed. How have all of these evolved? Back in the day of Babbage, there were no compilers or interpreters to translate the languages, so the binary code was fraught with error. Now there are compilers, and these compilers have highly detailed and efficient translators, now with IDEs and source code editors, minimizing the chance of meeting an undetected error and speeding up the process of code conversion with neatly indented lines and color-coded commands. With interpreters, the process of translating each instruction is quicker because of these modernized translators. With a quicker process, the assembly and high-level languages can be converted into machine code faster and easier. Also, there are more known and developed languages, be it machine, assembly, or high-level, for programmers to use.
So now you know what programming is, how it works, some of its key components, and even how these components have evolved over time. I hope hope you enjoyed this journey through 2,000 years of programming evolution.